All right, welcome everybody today for our TUM AI lecture. It's a real pleasure to have Alyosha Efros today. Alyosha is a professor at UC Berkeley, where he's part of the Berkeley Artificial Intelligence Research Lab, BEAR. His work is at the intersection of graphics and computer vision, and I'm sure pretty much everybody in the community has heard of him. He's a pioneer at the intersection in these fields. He has countless of exciting papers starting from texture synthesis to conditional GANs like pix-to-pix and cycle-GAN. He's particularly known for his creativity and thought-provoking work, which is an inspiration to many young researchers. His students have also had really great success. You can see many of his students are now professors themselves. And I think it's also, it's fair to say that he has also a very great social engagement, in particular contributing to the research community. If you haven't met him in person, I can only recommend reach out to him at the conferences once we have them again. It's really great to have him around. It's really great hanging around with him at one of the poster sessions and chat about some really exciting research. He's particularly known for his really cool attitude, and it's really great to have him as part of the community. So it's a real pleasure to have you here, and I'm really looking forward to the talk. And you also promised some philosophical components, so I'm really excited what that's going to be.
Thank you so much for such a gracious introduction. I'm sad that we have to do this virtually because I would love to have hung out with you guys and gone for some wonderful Bavarian beers but next time. Yes, thank you very much for inviting me, and it's such a star-spangled roster of speakers that you have there. I hope I will not disappoint. And so I'm going to talk about aspects of self-supervision. Self-supervision is something that my lab has been working for a number of years. And just to make sure everyone's on the same page, self-supervised learning is this is my definition. Hopefully there is no one set definition, but my definition is that it's when we use the tools of supervised learning, but where the labels are the raw data instead of being human provided. Okay, and so the question that often students ask is why use self-supervised learning? What's the point? Okay, and the classic answer, the common answer is because labels are expensive. Instead of having humans provide labels and annotating them using lots of hours of work or high cost, here we use the data itself as our labels. Okay. So this is the common answer, but that's not really my main answer. It's nice, but it's not the main reason for me. For me, I actually have a couple of answers. Number one answer is that self-supervised learning allows us to get away from the tyranny of this top-down semantic categorization that goes all the way to Plato and Socrates. Okay. And I'll tell you why I think this is a good thing. And the second reason is that self-supervised learning will hopefully enable us to move away from this idea of a fixed training set to a more continuous lifelong learning, where you have data streaming in and then you learn on the go. You learn as you live, rather than having this kind of training set, testing set split that is kind of the classic thing in machine learning. Okay, so I will start, and most of the talk is going to be about the first one, and then hopefully we'll do a little bit of number two. Okay, so what's the problem with semantic categories? Well, let's look at, from the visual point of view, let's look at a couple of categories from a standard visual data sets. So the first is what's called a chair. Okay, and you can look at all the different chairs that you could have in the wild, and you realize that this is very hard to find what is in common between all of these chairs, right? Visually, actually, there is pretty much nothing in common because between something like this and something like this, right? This chair is really more of a functional category, right? And think about it this way: we can see them all being chairs because we have seen, butts being squeezed into these places. But if you are a computer, if all you've seen in your life is ImageNet data set, for example, if you've never seen any videos, you've never seen any people sitting on anything, there is basically no way for you to realize that all of these are somehow related, right? So the relationship here is not visual. The relationship is functional. The relationship is that of affordances, and it's not really fair for a computer to try really hard to find a way to kind of somehow bring them all into some kind of a connection where maybe there isn't that much of a connection. Okay. The second example I like is this one called City. Okay, and here what I'm showing here is a picture of downtown Pittsburgh and a picture of the center of Paris. Okay, and frankly, the fact that both of these, by some fluke of the English language, are termed city, the same noun, this is just kind of a coincidence, because there is really nothing visually in common between those two, right? And people can argue, well, wait a minute, both contain buildings, but look at the buildings. The buildings are so different visually. There is nothing in common between those buildings, right? They're so visually different. And then you can say, well, but they both have windows. But again, look at the windows. The windows don't look anything the same. Look, there is really not a single pixel in common between these two things. And so again, we are forcing the computer to do something, to somehow try to generalize across these two things that are very, very different, that might not have anything in common. And so, and in a way, what we're forcing the computer to do is basically to cheat, right? It's kind of like you haven't attended classes, and then now it's your final exam, and you're trying to see what you're trying to cram for the final exam. And so what the computer is going to do is, like, anything that looks like this, it will be called a city. Anything that looks like this will also be called a city. But you're not going to basically get the concept of a city. You're just going to basically just remember the nearest neighbors, right? So basically, with labels like these, I worry that we're setting ourselves up for failure, right? We're setting our algorithms up for just memorizing examples and not really even having building connections between them, okay? Which is, of course, very bad if we want our models to generalize, right? If we just wanted to, train on ImageNet and then test on ImageNet, that's fine. But if we wanted to train on ImageNet and test on, the real world out there, then that's not fine. We need to somehow induce generalization, okay? And so this is where my promised bit of philosophy comes in, which is that I've been arguing actually for many years now, that we should step away from this top-down categorization paradigm and try to think more of it as a bottom-up association. And there is some movement towards that in especially in the 20th century. The philosophers have really kind of pushed away Plato's and Socrates' notions of these rigid categories, and really started to think about categorization in a much more bottom-up way. So Plato, of course, he argued that categories were lists of, they were abstract definitions with list of shared properties. And then in the mid 20th century, the philosopher Wittgenstein came out and said, no, this is that people don't do this. In fact, people are much more fluid about categories. And, for example, if you ask people, are curtains furniture? Are olives fruit? Different people will give you different answers. In fact, the same person might give you different answers different times of different times you ask them. Wittgenstein's classic puzzle was to ask people to name all what is in common across all games. What are the common properties shared by all games and not shared by non-games? And you cannot do it. It's just impossible. There's such a variety of games out there that you cannot think of any single thing that defines a game. It's not a definitional thing. It's much more kind of data-driven, much more bottom-up. Kind of, well, it's a game like football. It's a game like chess, right? And so in the second half of the 20th century, psychologists, in particular Eleanor Rosch, have tried to kind of update the notion of categorization and try to think about categories forming from the bottom up. And her famous prototype theory of categorization has really started this trend, where the idea was that you basically cluster, you do bottom-up clustering of similar instances into these prototypes, and the prototypes then get clustered again, and then you have this kind of a bottom-up hierarchy where the categories emerge directly from the data rather than being kind of this top-down. Okay, and later folks have psychologists have gone even further and argued for what they call the exemplar-based theory of categorization, where you basically you don't really have categories of any kind. You basically just store instances, store exemplars of everything that you see, and then you basically learn associations between those examples and the things that are closer together. Essentially, you can think of it as like this kind of a soft clustering of your exemplars into chunks, into groups, and those groups then emerge to be categories. And my favorite slogan is provided by neuroscientist Moshe Bar, who says, "Ask not what is it, ask what is it like." So this kind of this idea that association, bottom-up association, trumps this top-down labeling. Okay, and so this work has been very inspiring to me and my group over the years, and we have been kind of chugging away in this direction for a number of years. And maybe one of the earlier works that we did was with my former student Tomasz Malisiewicz, where we basically tried to kind of instantiate this exemplar-based way of thinking about categorization. And here the example, the idea is that we basically try to find per-exemplar distances given a set of data. So you have a set of labeled data, cars, people, pedestrians, trees, etc. And here, instead of trying to separate all cars from all pedestrians, for example, we wanted to basically learn a way to group every single instance of, say, car. So for this particular focal example of a car, we wanted to find what other things are close to it, right? And so those other things should be also labeled car, but there shouldn't be all cars, because this car, for example, looks nothing like this car. So should they really be in the same cluster, in the same category? Maybe not. And so the idea that Tomasz came up with was to basically kind of treat this as a kind of a classification problem, where you basically learn a decision boundary between things that are close to your focal example and things that are far. But here we actually have, instead of two classes, the ones that are inside of a category and ones out, we have three classes. There are the things that are close, and these are these kind of cars. There are things that are not cars, and they're on the other side. And then there is a third class, which is don't care. And these are basically other cars that might not actually be that close to the focal car. And then you basically optimize this decision boundary given some set of constraints. And as a result, what you get is something where you learn these distances that are that produce much more visually meaningful relationships rather than if you were just doing a standard set of distances without this. Okay, and so this was kind of a, we were very excited about this, but still we're still using the label card. The labels are still being used in this computation, and we really wanted to go away from labels entirely. And this is where Tamash's next paper came in, and this work, we call it Exemplar-SVM, was basically kind of a pushing this farther and really thinking about it in terms of classifiers, and basically switching from the standard classifier where you have class A and class B, instead to take every single instance, every single data point, and train a separate classifier for that one instance against everyone else, whether it's of your own class or a different class. So it's one against all classifiers. So this is kind of an interesting way to think about it, because it's really basically you're defining yourself not by who is in your category, who is in your class, but you're defining yourself by what you are not, right? So what makes you different from everyone else inside in your data set, okay? And then the cool result was that we were able to do one classifier for every instance and then ensemble them together, and the result was that this ensemble actually worked no worse in many cases than your standard standard two-class classifier like an SVM. Okay, and this was a little bit of a it was kind of like a bit of a trolling paper, which basically kind of tried to push the community to say, look, maybe you're not getting as much juice as you think you are from basically trying to group all those things into one class, because it seems like if you don't do it, you get basically as much of performance as not. Okay, and so we also use the same idea for retrieval. So basically, the idea is you take at runtime, you take your retrieval query image, and then you have a big data set, and you're basically training at runtime an SVM classifier to separate your query from everything else. Okay, and then you order all of your data based on that, on the coefficients of that decision boundary. Okay, you basically find who are the closest things, who are your support vectors inside of your data set, and those tend to be the retrieval examples. The kind of the closest ones on the other side will be the retrieval examples, and that also worked surprisingly well. And so we were very excited about this, and we were very hopeful. And then, of course, deep learning revolution hit, and all of this became irrelevant because much better classifiers came on the scene. We tried to update it for the deep learning age, and we didn't really succeed. But Alexei and colleagues did. Okay, so one of the kind of a very early influential papers was called Exemplar-CNN, which basically adopted the same idea of like one against all classification using neural networks. Okay, and the main difference that we didn't really think of was that whereas we used a single exemplar, one image against everything else, Desavitsky and colleagues, they used what's called data augmentation. So they took one example, and then they created a whole bunch of similar examples by basically applying various different transformations to it. Changing lighting, changing contrast, changing shape, changing various geometric transformation, etc. So in the end, even though all of these things came from a single example, they all were a little bit different, and so this became the positive class, and then everything else became the negative class, and that worked really, really well. Okay, and this work really was a kind of an inspiration for a lot of the current contrastive self-supervised learning that we are familiar with right now. So we thought we will be very pure and just use a single image, but this, of course, worked much better. And of course, now in kind of modern day, the self-supervised learning representations that seem to work the best, they're all based on this idea of similarity learning. Instead of learning which class you are, which category you are, the idea is to learn instances that are either close or far from each other. So learning the distances between the instances in your training data. Okay, so things like metric learning, SimesNet, and the new contrastive learning are all based on that same principle. So you have some sort of an embedding space, and your goal is to say, okay, for a given positive, like this particular instance of a dog here, you create a bunch of different positive example by data augmentation, and then you basically try to push all of them to be close to each other in this embedding space, and far away from other things, which are, dogs or other cats, etc. Okay, and this learning of the similarity is really what a lot of the contemporary self-supervised learning methods are doing. Okay, and so the reason why this, maybe like a year ago, this area really took off, one of the reasons is, of course, the improvements in the representation learning. The contrastive formulation is actually just works much better, as shown by papers like SimClear and stuff. But another reason, I think, that's maybe being a little bit underappreciated is that we are just much better at doing this data augmentation. So we have learned to do data augmentation in a better way than Dostoevsky in his Exemplar-CNN. Okay, for example, now cropping is a very standard trick for data augmentation, which wasn't a standard trick before, and that gives us a lot of boost. So again, what data augmentation is, you get yourself an input image, a single instance, and then you just randomly create a whole bunch of different versions of that image by applying a whole bunch of different parametric transformation, color transformations, cropping, flipping, blurring, etc., etc., etc. Okay, and then once you do that, then you set up your kind of a distance function. So you basically say that I want these two images that all came from the same image, really, I want those two images to be similar in our embedding space. So I'm going to try to bring them close together and farther away from the other images in my data set. Okay, that's really the whole story of contrastive learning. Okay, now the thing is that the choice of data augmentation itself turns out to be very, very critical. And in fact, I want to argue that this data augmentation is itself a little bit of supervised learning, because the way you choose your augmentation can make a huge difference in your final performance. Okay, so here is an example from our recent paper in iClear 21, where you can think of, let's say that you have different types of data augmentation, like color augmentation, maybe rotation, and maybe texture. Okay, so now we can look at different tasks. For example, if we want something like ImageNet, like course level categorization, then data augmentation with color makes a lot of sense. With texture also makes a lot of sense. But rotation is actually going to hurt you, because an upside down elephant is not going to be recognized as an elephant. Okay. Whereas if your task is, for example, fine grain recognition, well, then it gets even more complicated, because if you're fine grained the different species of birds, then actually you don't want any of those data augmentations, because they're all meaningful. Like changing texture may change the species, changing the color definitely will change the species. Whereas maybe if you're classifying different types of flowers, then rotation is fine, because rotation augmentation, because flowers are usually rotationally symmetric. Okay, And so you can see that it really becomes very, very task dependent. And another example is the cropping and image classification. So cropping for something like ImageNet classification makes a lot of sense because you have one big object in the center of the object in the image. But the same cropping for object detection actually doesn't make that much sense, because you crop it and you might lose where your object is. Okay. And so this is something that we started to worry about, because we feel like a lot of the advances in the modern self-supervised learning might actually be due to us being very good at overfitting the right kind of data augmentation for a particular problem rather than the actual methods themselves. Okay. So what we wanted to do is to try to do contrastive self-supervised learning without data augmentation, to really try to get it to figure it out on its own without this kind of help. Okay. And the way we wanted to do this is to make these augmentations, these what they're called views, to make them latent, to make the computer come up with its own data augmentation in a sense. Okay. And of course, the big question here is, this is all great, but where do you get the supervisory signal, right? There is no free lunch. You need to get some sort of supervisory signals from somewhere in your data. So where is it going to come from? And here I'm going to talk about a couple of papers where we answer this question differently. The first paper, the answer we have is that we want to use time as our self-supervisory signal. Okay. And here I have a wonderful quote from one of my favorite writers, Jorge Luis Borges, in his short story about fumes, who is this a man on the spectrum. He writes, "It irritated him that the dog at 3:14 in the afternoon seen in profile should be indicated by the same noun as dog at 3:15 seen frontally." Okay, so basically what he's talking about is that two different instances of time makes most of us assume that there is some continuity of what we are perceiving, that the dog and the dog here and the dog here, it's almost certainly the same dog, that nothing happened to this dog while it was jumping in the water, right? But humans, of course, couldn't figure this out, and neither can our computers, right? And so the idea is that this temporal correspondence, basically time as a way to align things together, to bring things into correspondence, is a very powerful supervisory signal that we should be using. Okay, and we have evidence that biological algorithms use it very strongly. There is plenty of psychology data for human infants that shows that temporal cues are very important to learning vision. And there is this wonderful line of work by Wood, who basically did this this experiments with newly born chicks. So basically, what he says he has is this kind of VR cave for chickens, for little chicks. So you put an egg, and then the chicken is born, and the chicken is born in this VR cave where he's basically projected things on all sides. So everything that the chick knows from birth is being controlled by the researcher. Okay, and what he showed, that some of the chicks were shown videos that were not temporally coherent, that basically broke this temporal continuity. As you can see, it was not kind of physically correct, and he compared them to chicks that were shown normal continuous things, and the chicks who were not who saw these discontinuous patterns, they were not able to function in the world as well. They lacked some of the visual perception skills. So that showed that this is extremely important. This temporal continuity is extremely important. Okay, and so what we want to do in this work is to use video as data augmentation, as a way to to create these data augmented views ourselves. Okay, and basically the main thing, of course, is that this can provide correspondences across different instances and allows the computer to learn how something looks across time change. Okay, but it can give us even more, because we can also think about contextual relationships and notice things that are moving in the same way, what Wernheimer called common fate, and also use that as a way to group little points, little trajectories into groups, and maybe get to the notion of objects from the notion of points. Okay, again, something that you can use temporal information for. Okay, and so this is basically the story. And then the question is, how do we harness this information without any sort of supervisory signal? Okay, and in the past, people have used things like slow feature learning, where they basically kind of looked at connecting nearby frames together, basically look at nearby frames as the positives and faraway frames as the negatives, but you just collapse the entire frame, and so that's not really something that can give you like these point tracks. It's much more coarse signal. Alternatively, people use things like optical flow or tracking to create correspondences using some off-the-shelf methods, and then use learning to connect things that are supposed to be in correspondence. But here we're, you're using two different methods, and so what we wanted to do is do something like this, but kind of in one go, in one packet. And this is our paper that tries to do this. This was published in NeurIPS this past year. And here is the idea. Okay, and so for a warm-up, let's consider the case where you actually do have labels. Let's say that somebody went ahead and labeled that this patch corresponds to this patch. Okay, and your goal is to basically learn a representation that brings things that are the same into correspondence and away from things that are different, right? So in this case, of course, it's very simple. You just say, okay, these two things are my two positives. I want them to be close together. And all the other patches are my negatives. I want them to be pushed far away. And then you have your standard self-supervised learning, contrastive learning problem, and off you go, right? Nothing very exciting. Now, things get a little bit more exciting if you have maybe another frame in between, okay? Because now you have, these two guys are your two positives. We know this by labeling, but also because this is a video, we know that from here somehow it needed to go to be in this final place, and so there must have been a path, the most likely path for this guy to go from here to here, and the most likely path is going to go through this patch. So it's reasonable to assume that this patch should also be in our positive category. It should be in the same category as this guy and this guy. So now these triplet should be the positives and everything else should be the negatives. So now you can think of a little bit of kind of automatic data augmentation, that this guy, just by virtue of being tracked in the video, becomes a data augmented positive for our case. Okay, so this is okay, but this is still requiring us to have this supervision. How can we get rid of supervision? Well, we are going to use our old trick, which we've used before, called cycle consistency. And what we're going to do is we're going to make this video into a palindrome. Palindrome, if you remember, in language, is a word that you read it forward and backwards and it reads the same, right? So how can we make a palindrome out of a video? Well, what we can do is we can take this video and flip it around and put it back in reverse order. Okay, so now what we have is we have something like frame 1, frame 2, frame 3, and now we're going back to frame 2 and then frame 1. Okay, so now we have this new video that's a palindrome, and look what's happening. Now the final place, the destination, is now exactly the same as the origin by construction. So now we don't need supervision anymore. We got rid of supervision. All we need to do is to get from the blue guy to the green guy. And the way we do it is we're basically trying to do a track through this video, and everything that's on this track should be in our positive category, and everything else should be in the negative. Okay, and so now you can see the setup where we basically, are getting something out of nothing. We're getting some supervisory signal just from the mere video information. Okay, so basically the story is that we're going to take a video, we're going to make it a palindrome by going from t to t plus k and then minus to back to t. We're going to make it into a graph. We're going to turn the video into a graph. Okay, and then we're going to walk along this graph until we get to the end. Okay, and we're going to do basically a random walk on this graph, and then we're going to steer that random walk such that if you start from this blue point right here, we want to steer it to get us to this green point right here. Okay, and this is going to be our only supervision. The supervision is going to be at the last frame, where we're going to say that the positive is going to be anything that lands on the green dot, and negative is going to be anything that lands anywhere else, anywhere on this red dot. Okay, and that's basically going to be the signal that we're going to use. Okay, so and also notice that we don't have to have a single path through this graph. We kind of naturally we can incorporate probabilistic information by tracing many paths through this graph. Okay, so how do you turn a video into a graph? Well, it's kind of a standard thing. You create nodes, and then your nodes are some representation and some using some encoder phi. And really, this phi is really the only thing that you are learning. What you're learning is the representation of each patch in your feature space, and you're basically trying to figure out how to arrange those features in your representation. Who is going to be close, who's going to be far. Okay, and so your video is going to be a graph, and then from frame t to frame t plus 1, you're just going to have a transition matrix that's just going to say, where did all the points from t go in t plus 1, and then this is just basically like a dot product in the feature space. So the closest things are going to be to get the higher dot product. Okay, and then how we're going to do a random walk? Well, just going to compose all of these transition matrices A, just like in a standard Markov chain. You're just multiplying all of those transition matrices, and you get your full walk on this graph, right? So now, kind of the nice thing is that the task of learning this representation phi is essentially the same as fitting these transition probabilities. Okay, you find the right transition probabilities, and that gives you your representation phi. Okay, so again, in kind of if we do have the target somewhere, if we do have the supervision, then this is just a standard contrastive learning problem. You want to find a representation where this query goes directly to the target and doesn't go to the red ones, right? And this is basically just, this is your positive, these are your negatives, this is your standard contrastive learning problem. If you have multiple frames in between, then in a sense you have some latent views that you can also use, right? So now we have, these are all the positives and these are the negatives if it's an obvious path. But if you have multiple high probability paths, then these will be weighted positives, and these will be weighted negatives, and you can still do it. And so again, from a single point of supervision, you get all of this data augmented information. Okay, and of course, what we can do then is we can do the palindrome trick, and now we get all of these latent data augmented positives without even providing any supervision. Okay, because this is basically by construction, the target is the same as the query. Okay, And so we can just set this up at training time, and you can see that it's if you pick a point in the query image in a simple first image, you can see that over time it kind of gives you a little probability distribution of where that image might have gone. And you can say, well, maybe we can even do this by trying to get grouping happening and find out a group which corresponds to a single object. And to do that, we have a little extra thing that we can do, which is we can do dropout. We can cut some of the edges away and force the correspondences to go through nearby paths. And that basically allows us to get a little bit more of this kind of grouping happening, where you basically kind of you go through the paths that are also on the same object. Okay, and we basically evaluated it at the runtime by essentially nearest neighbor in the phi space. And here are some examples. This is the kind of the state of the art label propagation results, and these are the results of our methods. And you can see that it's basically behaving much better in terms of occlusion handling, and it seems to do quite a bit better. Here is again state of the art self-supervised method, and this is ours, right? Even against supervised methods actually does pretty well, even though it doesn't get any sort of supervision. So here is kind of an example of how we do compared to some of the self-supervised competitors. And interestingly, even for methods that are trained on image using ImageNet representation, we are actually doing better than that. Okay, and here are some examples of kind of propagating various things like skeletons or labels or things like this. Okay, so this is one way to use this contrastive learning as without data augmentation. But of course, in my lab, we also like to make pretty pictures. And so I'll briefly show you another way of using the same kind of an idea of kind of creating your own latent views for an image-to-image translation setup. Okay, and here the idea is, of course, unpaired translation. The classic thing that we've been doing for a while. We want to translate horses into zebras, but we don't have a correspondence between horses and zebras. Okay, so we want to go from here to here, but we don't have a correspondence. Okay, and of course, the one powerful signal here is we can use a GAN loss, which basically says make this thing into a zebra by basically forcing it to look like other zebras that I have seen, okay, using a GAN loss. But that GAN loss is not enough, because it can make it look like a zebra many ways, right? But we want it to kind of be in correspondence. And so this is where we also want to have another constraint. And in the past, in works like CycleGAN, we use the cycle consistency constraint, which says, okay, make it a zebra, but also make it so that when you translate it back, you'll get back to the original horse. And that's kind of forces this to be the right answer, not these. Okay, but there is a problem with this cycle consistency constraint, because the problem is that it forces it to be a bijection. It forces it to be one-to-one, because yes, it's not going to go back to here, but it's also going to constrain us to have to go back to this particular horse, whereas these other horses might have been just good enough, right? So this is where kind of a bijection is not always desirable, because sometimes these cycles are not a bijection. So how could we kind of address this problem? And here is the approach that we came up with, which is we are going to have an image-to-image translation framework. We're starting with our horse. We want to get a zebra, so we have a GAN loss that says, okay, make this a zebra, okay. And then what we're going to do in addition is we want to make this zebra to be similar in structure to this horse, but not in texture. And what we're going to do, way to do this, is we're going to enforce the structures to be the same by taking pairs of patches across the input and the output, and say that these two patches need to be close to each other in feature space and farther away than other patches from the horse image. Okay, so you can see that again we're getting this whole similarity learning story here, where we are basically bringing these two things to be closer and farther from the other patches of horse. And again, just unlike other methods where the positives are somehow automatically created by data augmentation, here the positives are basically our input and our output. So the output becomes our data augmentation. Okay. And now we are back into our contrastive learning land. We just basically formulate this, and we basically say learn a representation such that these two guys are close. So basically it kind of ignores the texture and focuses on the structure, and these things are fun. Okay. And of course, what we do this, we don't do this on just on the pixels. We do it at different levels of representation, at basically different many multi-scale patch representation, and we do this contrastive learning basically everywhere here in our decoder. Okay, and of course we also have our get losses as usual. Okay, one kind of interesting, cute note for those who are in this might appreciate this. Well, we thought, okay, the positives, that's everything's clear. With negatives, we just take all the patches from the same image. And then we thought, maybe it will be better if we take the negatives to be not just patches from the same image, but also just add other patches from other images, other negatives, right? Should be even better, even more negative data, right? And guess what? It turned out that this did not work as well. These external patches actually made performance worse than if we just kept the internal patches. Okay, and this kind of goes back to some old work that I have been doing on texture synthesis, where we also seen that patches from the same image actually provide much more information than if you start mixing them up with patches from other images. And in fact, Michal Iranik has this wonderful example story of doing super resolution using a single image, where she shows that you can do it super resolution by learning from a single image. You basically take an image, downsample it, train a CNN to upsample that one image, right? So you basically train a single image network and then just reuse that network for the original image. So that works better than if you're training a standard thing with a large data set. Okay, and basically we're seeing the same thing happening here, that it's actually the patches that are in the same image, that have the same illumination, the same camera parameters, the same setting, they actually much more powerful information than if you just put a whole data set. So this is kind of a cute little story, and you can see here how using the internal patches we get much better translation than if we use external patches, where you can see that there is a lot of mode collapse happening. Okay, so yeah, so basically that's the story, and this is our method, and compared to something like CycleGAN and other methods as well. And basically we see that we're basically getting as well performance, as good as CycleGAN in most cases, but it's much faster, and it's one-sided. You don't need to train two-way thing, and it's basically we think it's kind of a much better story. And so here are some of the transformations that we have. And one cute thing that we can also do is we can basically apply this to instances. So for example, let's say that we have a single image, Claude Monet's painting. We want to make it into a photograph. And maybe what we have also is a single image. Instead of a data set, we have a single photograph that is also, let's say, of water lilies. Okay, well, we can basically use the same kind of contrastive learning, basically just between a single reference photo and our output. Okay, and have one have the same thing here for the positives, and have instead of a GAN, have basically just a single discriminator here, and we can get something that actually works quite a bit better than a lot of these kind of stylization methods. Okay, so this is competitors, and this is ours, and I think that ours actually looks quite a bit more natural and also better than CycleGAN. Here are some other examples. Okay. Let's see what timing is. Well, I don't think I have time to go over the second point of why use self-supervision. Maybe I'll just give you a little bit of a hint of what I mean, and then you can read the paper if you're interested. So basically, the idea is that it's a little bit weird that we're in most of machine learning, we're using a fixed training set. It's not very natural biologically, because biological agents, they never see the same data twice, right? So you live your life, you never see the same thing twice. You see something first, you deal with it, you hopefully learn from it. If you didn't deal from it, you're dead. If you deal with it, you learn from it, and then you kind of recover some information from it, but then you never see that again. You see maybe something similar. Okay, so every new piece of data is basically first in your test set and then in your training set. Okay, and it seems like using a fixed data set, it kind of encourages memorization because you see the same exact thing over and over and over again. In fact, maybe this is actually another reason why data augmentation works, because data augmentation is kind of random. You create a random thing every time, so you kind of get away a little bit from this memorization. So in fact, this might be kind of a subtle way in which data augmentation helps, that actually has nothing to do with the data augmentation. It's just basically randomization of your data. Okay, but the point is that if you're using self-supervised learning, like the whole point of having a fixed training set was because it was expensive to do all these labels. ImageNet, poor Fei spent all of her startup money in Stanford labeling this huge data set, right? So it kind of makes sense that it's fixed because it took so much money to label it. But if you're using self-supervised learning, if you don't need the labels, what's the point of having a fixed data set? Why can't we just keep downloading images from whatever, the internet, the TV, whatever, and just keep doing it all the time because we can generate our own labels? Seems kind of natural. And so this is where kind of I've been pushing on this idea of kind of this online continual learning. So you can think of it in terms of the standard train val separation. So you have your training set, and kind of the standard thing in machine learning is you can separate it into a training set and a validation set, right? And we know that if you just train on the training set and then use the validation set to tune your hyperparameters, you usually get better performance on the eventual test data than if you just train on all the training set all at once. Even though you're kind of you think that it's less data that you're using for training, but actually this is turns out to be more effective. Well, we can think of the same thing in a continual way. So we can think of it as you train on the data that you have seen, and then you're validating on the next data that comes along. Okay, and then once you do that, you just incorporate it into your training set, and you can keep going, and it can keep going on forever. You don't ever need to stop. Okay, and this, I think, is a kind of a very powerful trick that is made that we can now do because we can use self-supervision to do this evaluation, this testing. Okay, and so this is the idea of test time training, which is our attempt to operationalize this on an infinite, smoothly changing stream. And the idea is to basically use self-supervision to continuously adapt to new data. Okay, and we did this already in the case of reinforcement learning with our curiosity work, and this new work is basically trying to do it for images. And this is the paper, test time training, and it was in ICML 2000. Maybe just give me. I'll give you one slide of intuition of what we're doing. Basically, the idea is that we're let's say we have a training set of, I don't know, object detection, right? And at training time, we have our standard thing, we have our image, and we have our label, so nothing new here. We have a input in, label out, we're training a detector, and then at the same time, we also have a self-supervised head that basically, given your image, it does some self-supervised task. In this case, we are basically, our task here is rotation prediction. Given a rotated version of the image, we want to predict which rotation it is. It doesn't really matter, it could be any task at all, okay? So at training time, we do both of those tasks together, but then at test time, of course, we don't have the labels, but we still have this task, okay? And so we can basically run this, we can evaluate this task, and if the result is not good, if it failed this self-supervised task, we can do a little bit of fine-tuning, a little bit of fine-tuning training for this other task. But as we're doing the fine-tuning, it's going to change the representation in a way that will also impact the real task that we care about, and that allows us to do better as we are changing, as we're going through the data set. And so here is an example where, given this image at test time, basically the right label is elephant, but initially it basically thinks it's a dog. But then as we do this fine tuning on our test, on our self-supervised task, it figures out that it's actually less of a dog and more of an elephant, and gives us the right answer. And that's basically the story of the paper. Sorry, I had to rush, but you can look at the paper online. And to conclude, why use self-supervision? One reason that I like is that it allows us to get away from this top-down semantic categorization and gets us more into this bottom-up association story, and learn things from the bottom up. But we must be careful that the supervision doesn't leak in through things like data augmentation, right? And we need to be careful about this. And second is that eventually self-supervision should enable us to check the data sets, forget about all these fixed data sets, and learn things continuously. It's we're only starting on this direction. I think it's very exciting direction, very exciting problem. So I'm hoping people will get excited about it. Okay, thank you very much.
Yeah, awesome, fantastic talk. Thanks a lot for all the amazing works. Yeah, self-supervision is cool. Does anybody have some question on Zoom? Maybe let's start with this. We have a lot of questions on YouTube, but I'm going to start with Zoom. I have a lot of questions too, but if somebody wants to ask a question on Zoom, just turn on your video and just speak up probably. I can start with maybe a high level question first. So, I mean, the challenge in self-supervision is, right, you basically have visual data and you, let's say, correlate patches with whatever contrastive loss or whatever people do now. I mean, what do you think about, if you're thinking about the 3D world, right, you have obviously a third dimension. Is it a smart idea to do this actually all on images and videos and not think about, I don't know, like kind of project a 3D representation maybe first, and then think about how to kind of get similarities in some 3D space, learn a 3D representation, and then try to generalize with a downstream task later on.
Right. No, this is absolutely, and as you know, I've been angling for going into 3D, since a long time ago, since our work with Derek Hoym on qualitative 3D. I'm a big fan of 3D in my heart, and it's kind of a little bit sad that once we went to neural networks, the kind of things dropped back to 2D plane for a while, and now of course they're coming back again. Okay, so there's two answers to this question. One, the final, the ultimate answer is that 3D should emerge from our 2D observations. The representation should figure out 3D on its own, okay? Just like it's done with humans, right? Humans are only seeing 2D projections of the 3D world, okay, if you have stereo, maybe you have a little bit of 3D, but I don't have stereo, for example. 10% of people in the world don't have stereo, and we are perfectly fine seeing 3D. Okay, so we learn 3D from a series of 2D representations, and I think if we go from collections of images like ImageNet to videos, for example, hopefully, and I'm very hoping that it will encourage 3D to automatically emerge as the inside of the representation. Okay, so that's kind of the glorious answer at the end of the rainbow. Okay, but of course this is very hard. This is kind of a very tall order, and we are seeing a little bit of this happening. We are seeing a little bit of kind of a maybe 2.5, 2 or 2.1D kind of conclusion reasoning, figure ground reasoning, a little bit of that, but we're definitely far away from that, right? And so the second direction is, okay, can we kind of help it out a little bit? Can we provide features that are more amenable to three-dimensional manipulation? And there, I think things like hologan or pygan, this kind of directions are, I think, very exciting in that it's kind of you kind of inject some things that are physically true, like rotation, for example, and so I think in the short term, all of those things are, I think, going to be extremely helpful. In the long term, I'm still kind of hoping that I can learn 3D from scratch. Okay, but who knows? Maybe it's too much to ask. But I'm still kind of hoping that one day I will wake up in the morning and boom, my computer learned 3D. But we'll see.
Do it with 2 cameras, right? We have stereo. That's, I mean, it is.
Well, no, that's the thing. Like, I don't have stereo, for example, right? Like 10% of people don't have stereo. Okay. Stereo is actually not as important as we think. Stereo is only really important for like the half a meter in front of you. It's like what is it that I cannot do that everybody else can do? Okay, I cannot put thread through the needle and I have trouble pouring wine, right? Other than that, I'm fine. So really, stereo is kind of overemphasized. I think it's really parallax is much more important, and parallax you can get from video.
No, good point. I have another follow-up question. So in a similar spirit, right, like one argument is you can do contrastive learning, and mostly it's about comparing things, right? You're saying one versus all classifiers, like how similar are these things. I mean, what about going back to the original things when people using like autoencoders for pre-training and so on, for like basically using generative tasks? Let's say, oh, I trained my favorite GAN. How good of a representation can I learn from learning the distribution, basically, right? Like how well, like it's like this famous thing, like you have to be able to create in order to understand. And where do you see that competing or maybe going along the same lines? So what's your take, generally speaking, on the lines there?
I mean, yeah, we have definitely been also using autoencoders as well. I think with an autoencoder, it's a little bit of a it's a little bit of a magic box. Like if you get really lucky, your autoencoder is going to capture exactly the right things, and if you get unlucky, it will capture exactly the wrong things, right? It's kind of a compression mechanism. It somehow compresses your data, and it really depends on what you care about. Like sometimes it will compress away the stuff that you care about, or sometimes it will retain the stuff that you care about. And it's a little bit hard to control what it's going to do. So I think this kind of a similarity learning it allows you to get a little bit more control and a little bit of more of kind of a intuition about what is it being learned. And it's also kind of has a very nice connection to graphs and graph theory, that kind of you think about it like you have different entities, and then you have kind of, you can think of it like as a network, right? Like a social network, for example, where you can think of different people being connected in different ways. And you can think about, yeah, we call them senses of similarity. So there's many different senses of similarity between two instances. And something like an autoencoder is probably going to collapse them all together. And here you can actually separate them. You can have a similarity in color, similarity in texture, maybe similarity in 3D, and they're all can be kind of exposed, hopefully separately.
No, that's interesting. I mean, our experiences, so we've done a lot of stuff on like shape completion in 3D. So whenever we had the ability to take stuff away and predict it, then we got great features. This was always amazing in terms of using these features to help semantics. And whenever we trained a classifier to help the completion, this is always a total disaster. It never worked. We tried really hard, actually.
I mean, I think that's been our experience as well. But I think have you tried the latest contrastive learning? Because it's really to me, the way I think about contrastive learning is it's really just old school triplet loss, Siamese network learning, except you're switching from kind of a regression to a classification, but it's a classification with like huge amounts of data, and it's very, very fine-grained classification. So it's almost it's really not like your grandma's classification. It's I mean, we did something like this for when we did colorization. So we first tried to do colorization with the regression, and then we got better results by doing classification. But the classification was across like 500 classes of different colors in the color gamut, right? So it's a much more kind of narrow thing, and that seemed to work for us. But yeah, like if you have a few classes, then it's very hard to make it work. But if you do something like either have lots of classes or do something like contrastive learning, where it's basically just really kind of push it with data, that it seems to work for us.
No, we've actually tried that. So we had one student project actually in collaboration with Fair. So Jihu, one of my students, they've been working on basically doing contrastive learning for pre-training 3D structures in a similar way than you would do it in 2D. It does help, but the completion still seems to work a bit better. It's very interesting.
I think so. In general, yeah. I mean, I think if completions, if actually predicting pixels or predicting voxels, whatever, it has more data. It has more information. And we know that 3D world is actually much, it's much more informative, right? So, and it's also, I think, much more unimodal. So the one thing that was hard for us, for example, when we did colorization, is that we're trying to colorize a bird, and the bird could be yellow or the bird could be green, right? And so you have multimodal, you have two modes, and if you're doing kind of just like a regression completion, what's it going to do? It's going to do the average, right? So it's going to be neither here nor there, right? But if you have a single mode, it works really well. So it might be that in 3D, you're really in a world that's much more unimodal, in which you don't have you're not trying to have an average between two different completions and you get something that doesn't look like either, but you're actually really focusing on a single mode. So in that case, maybe this is why you're getting better results. But I suspect that if you had multimodal, like if you have a hole that's big enough that you could have many different plausible completions happen to it, I suspect that then your kind of the prediction route might have more problems.
No, I fully agree with you. No, that one is definitely true. But most of the case, right? You're thinking about, it's more like a dropout in a sense, right? So you're leaving out some stuff, right? And then you're trying to figure out what's missing. In this case, I think we've experienced that it works remarkably well. If it's too large, then you need probabilistic models again and stuff like that. Right. Then it's a lot more difficult.
I agree. Yeah, I think it's kind of if it's a level of dropout, then it should just work. Yeah, I agree. Yeah. I think if it works, you should definitely use it. Absolutely.
Actually, any other questions? Maybe somebody else can ask questions. I don't want to dominate the discussion too much.
Hi. Yeah.
Hi.
Thanks for the talk. I have similarly high-level question. So speaking along the lines of like multimodality and stuff like this, it seems like you have a lot of inspiration in terms of how to learn perception based on how people perform perception. And it seems like people do have naturally some kind of estimate of uncertainty, multimodality, and the ability to generate also for like these video tracking kind of applications that you showed, like multiple hypotheses for where the predictions should go. And how far do you think you can get without this explicitly modeled, or do you think it needs to be explicitly modeled?
Good question. I think I would go with I don't know. So yes, humans are very good at modeling uncertainty, but I don't think they are doing it in the way that statisticians do it. I don't think humans are actually probabilistic. I think they might be doing it almost like, if you remember from a long time ago, like all this particle filtering, where you can keep a whole bunch of hypotheses and then you kind of keep all of them going for a while, and then you kind of drop one, like, you know, there's illusion of like young lady, old woman visual illusion, where, you know, one time you see like an old lady, one time you see a young woman, right? And you never see both of them. So it seems there's some very interesting mechanism going on, but I think it's not like a standard probabilistic mechanism. And so yeah, so I don't know how to deal with it. And in this video paper that I showed, you know, we are really just keeping a whole bunch of hypotheses as we're going through the video at training time. At test time we don't. And but whether that's the right thing to do or not, I don't know. I think it's a very important question. I don't have an answer, but frankly, I think that nobody else does either.
Sounds good. I think one other somewhat unrelated thing, I think there's a bit of a tension between people who think that we should be able to learn everything from scratch, like you mentioned, in terms of being able to learn 3D, and whether this is actually possible, because it's unclear, I guess, how much supervision, certainly for like semantic perception, people get direct supervision. And
well,
so
yeah, okay, now we're back to philosophy. I think it must be possible because it already happened, right? Supervised learning is something that happens in nature, but it's very, very rare. Like parents teaching their children things. I know that a lot of modern parents, they feel like it's super, super important. But sorry, you know, developmental psychologists disagree. They say that it doesn't really matter that much. Most of the things that a kid picks up, they pick up without supervision. They pick up on their own. And you could think about it, you know, from in the very beginning, right? In the beginning, if you're, you know, as long as you believe in evolution, you must believe in unsupervised or self-supervised learning, because in the beginning there was nothing. There was no teacher, there was no supervision, there was only data, right? And kind of the organism and its environment were co-evolving and learning from each other and developing. So I think there is to me, there is no question that it should be possible in theory. I think that the interesting question is does it make sense to do in practice, right? And like you could also say, well, why don't we just simulate evolution for a gazillion years and then we'll get everything, right? And that's of course not feasible with the current technology. So I don't think that there is that much, or maybe there shouldn't be that much tension, because I think there are people like me who really want to try to learn things from first principles, and I think this is very interesting, if anything, from the biological plausibility point of view. Okay, and there are people who just want to get stuff done and get to a good result fast, and those people should definitely just use whatever works best at the time. So I'm not sure that it's either or. I think both directions are are useful, and I think we're learning from each other. I think those two directions are informing each other. So for example, for a very long time, self-supervised approaches worked worse than supervised approaches. And so, if, we could have all quit because, oh my God, our stuff doesn't work as well as supervision. But we persevered because we thought that, there's something interesting that we can learn anyway. And now what we're seeing is that for some tasks, self-supervision actually works better than supervised learning. Not for all, not for many, but for some, there's definitely some cases when it actually, the learning from the data actually gives you better results than learning from labels. And so I think let all the flowers bloom. I think both directions are useful, and I think it's great that people are pushing in both of them, and I think we'll get to a better point eventually, and we'll learn more. So I'm actually optimistic on all fronts. It's not a competition. Well, it is a competition, but it's not one is right and the other is wrong. I think both are right.
Cool. All right. I think that's a very good I guess ending of the live stream. I think thanks a really lot for the amazing talk. We're a little bit over. I have to apologize to a lot of questions on YouTube. We couldn't unfortunately go into all of them, but it was really great to have you. And I hope also for everybody who's here right now. Next week we'll have another great lecture with Raquel, and yeah, we'll see. So thanks a lot again for the great talk and great research. Okay.